All right, thank you very much for the presentation and for the introduction. It's great to speak at this conference. I want to talk about the work with Ken Larson and Sam Canning about trying to understand the cohomology of empty and bar from the sort of, I guess, Motivic point of view. But anyway. I was say, so the starting point of the theorem to the top comes from the Langdon program. And so maybe I can say a few other names associated with this relative idea. The idea is roughly the following. There should be a bijection between motives. I'm going to be purposefully vague about what motives means. Motives are here in the cohomology of smooth, proper linear stacks that are defined over the integers. So this means that they have to be smooth and proper over the integers. And on the one side, so you have this cohomology type data. So motives should just mean to you roughly about what the cohomology looks like. And then on this side, we get a bunch of adjectives: polarized, algebraic, custodial, automorphic, representations of PGL and I guess of PGL in general, of conductor 1. And okay, so most of us are algebraic geometers. I think this side, the correspondence, is easier, at least for me. This is a bunch of words, and you don't have to know what they mean. But one thing is that conductor 1 corresponds to this being smooth and proper over all of the integers. And okay, so why do I bring this up? The point is that actually the number theorists and representation theorists are good at understanding this side, at least when the cohomological degree is small. So the representations on the right-hand side have been completely classified in Motivic way at most 22. And this is work of Goethe, and Ron, and Renard. And there's more work. Okay, so what does this mean? It means that there's some list that the representation theorists can give us, and that tells us what should appear in the cohomology of any smooth proper stack over the integers up to H22. So H22 and below, we should completely understand what's happening. Conjecture based on this Langland's correspondence. Okay. Does anyone know a smooth proper stack of integers? There's one on the board, but they're hard to find in general. So, for example, when I first learned this, I haven't revealed it. This is actually a pretty short list. I'll write it down in a second. When I first learned this, I just thought it was false because it's ridiculous. But actually, the reason is that being a smooth proper stack over the integers is a really restricted condition. And the idea of this talk is to try to test whether this correspondence is true in the case of MGN bar. So can we actually see that this is all the ones over here that have been classified are all you're going to get in the cohomology of MGN bar? So let me tell you a little bit about the predictions. So the subject of this talk will be in Motivic ways and most 15. There's very few possibilities. So all the motives, all these motives are Tate twists of 1, delta 11 and delta 15. So let me tell you what these are. So delta 11 is the motive associated to cusp forms of weights 12 for FL3V. So when I say motive, basically what I'm going to mean by this talk is kind of a choose your own adventure thing. So if you're a complex geometer, you should just think of an odd structure. And if you're an arithmetic geometer, you should think of a Galois representation. So this motive is, for example, if you're a complex geometer, this motive delta 11 is actually just H11 of M1 11 bar. And as a odd structure, after you tensor with C, this decomposes into just two one-dimensionals. So you have a holomorphic form coming from these modular forms for SLTP. Okay, and delta 15 is exactly analogous, but replace 12 with 16. That's all I could here in this small motivic weight, and then you can take twists, so you can always have what should be conjecturally algebraic cycles in convention, in motivic weight 2, 4, 6, 8, etc. Yeah, it grows, so I can write some down. So the extra ones are 17, 19, this kind of 17, 19, those are defined analogously. And then there's ones that come from Siegel modular forms, so weight 2. So the indexing, I have a hard time keeping track of, but it's something like this. There's a few more. An interesting one that comes to me, and weight 22 is the metric product of delta 11. So these things are cusp forms. These ones are cusp forms for SP4. So okay. So what does this predict? So first part of the prediction is we see that nothing in the small list appears in odd weight below 11. So the first prediction is that if K is at most 9 and odd, then we should have K of MGN bar vanishes. The second thing is that if K is less than or equal to 20 even, that's coming from this list, we should have the cohomology of MGN bar is pure K. So if you believe the Hodge conjecture, you should believe that these groups are generated by algebraic cycles, which seems pretty reasonable for MGN bar, but Who knows? And then the last thing that I'll say is that H11 and H15 should only have non-zero Hodge groups up for the border. So the only things that should be non-zero are H11 0, H011, H15 0, and H015. So this is a lot of vanishing of odd numbers.
So all these expectations come from the correspondence?
Yes.
So because you know what happens on the right.
Exactly, yeah.
So in a statement about the Motivic weight at most 15?
Yeah.
That's a statement on the left-hand side, or you can I'm in this statement here, I'm just listing what Schneider and Long have proven in Motivic weight at most 15 on the right-hand side. And then you say this should correspond to what you prove. Yeah. So essentially, none of these things is proved at this point. Yeah, yeah. So that's what this talk will be about. But that's for MG and bottom. So one thing that is proven completely is this expectation for Motivic weight 1. This is a paper of Fontaine called "There are no abelian varieties over the integers." So this prediction is that H1 of any supercopper dream of the stack over the integers should vanish. And this is translated into there are no abelian varieties over it. Okay. Oh, sorry. And this, then you can also teach with these. These can also be non-zero. Okay, so I can tell you here, there's some theorems now. So what do we know about these predictions? So the first one is due to Argyle and Cornelva, and this was way before this Langland story connection to MD and bar was understood at all. So their theorem is that if K is 1, 3, 4, 5, then the cohomology vanishes as is predicted by this general philosophy. And this was in the early 90s. And there's a recent breakthrough, I think that was on the archive in 2022, by Jonas Bergström, Carl Father, and Canning. Which says that if K is equal to 7 or 9, you also get the vanishing. For all of yeah. Yeah. Can I ask another question? What I mean, is there any a priori reason why on the left-hand side we should only be looking at cohomology of MG and bar?
No. You should look at anything that is a smooth copper gleam up a stack over the integers. They're not so easy to find. So for curves, there's only P1. You need to have good reduction everywhere. It's very difficult.
Yes. Yeah.
So I know like 2 of them. You know, I know MGN bar and AG bar for a good choice of toroidal convexity.
But in principle, there could be some completely
certain.
Okay.
Is there another question in this area?
Are any of the KSDA spaces defined over the integers?
Yes, at the moment they're defined, like some of them are when you infer there's a very small number of primes. So there's if I replace this conductor 1 with another number, that's another small number, then this correspondence should roughly work out. But then there's going to be more representations and they haven't been totally classified except in really small ways. This is our best. Yeah.
since we're about to ask these kind of questions,
are all the others that have been realized, do they appear for some given stack over Z? I mean, it's sort of the realization part of that correspondence. That
all the ones in Motivic weight and most 22 appear in the cohomology first. Okay, yeah. But roughly, because they all come from modular form, so they appear in the cohomology of maybe modular nucleic, right?
Yeah.
Yeah. So, okay. Cool. Okay, and then so I can say now our theorem. Okay, so this was 2022. And then we proved recently that all of the predictions are correct. For K, then more 15. So what does this mean? This means that if K of MGN bar, where K is the most 15. So if K is even, then this is Kate. So if K is 11, then the only motive that can appear is this delta 11. And then finally, K 15 gives you that the motives that appear are delta 11, K twisted twice, or delta bit. That's the only possibilities. So this is like a theorem that's if you like concentrate that says like that in its odd cohomology a lot, you get a lot of vanishing of the very odd groups.
Sorry, Sam, can I ask you?
Yeah.
Why is there no H1, 12, for example, in that list?
H1, what?
Like, why can't you twist by the state not if only one?
Oh, I didn't say K is 13. Thank you. So you can then automatically get delta 11 answered with 1 8. So, yeah. There's no you would think that there should be delta 13, but there is no weight 14 customer thresholds. So yeah, thank you. Okay, so I want to explain how to prove these types of statements in this talk. Okay, so the central idea in all of these theorems goes back to Arbroath and Pernava, and it's to do an induction on G and N based on the stratification of GM bar by topological scientific variable. So the Arbroath and Pernava induction is just based on looking at the long exact sequence in compactly supported cohomology for MGN, MGN bar, and its boundary. So we look at this long index sequence. The idea is simply that if this one vanishes, then the cohomology of the stable moduli space injects into the normalization of the boundary. Okay, so why is this a lemma and not an exercise in homological algebra for your algebraic ecology students? The reason is that I had to put this normalization here, and that's going to help us make the induction work. So it's a little bit of Hodge theory to show that you get this. And the point is that the normalization of the boundary decomposes as a disjoint union of things of the form n minus 1 n equals 2 bar to has two actions. So I can take a curve and glue it to itself, or I can take I can take two curves and glue them together along a mark point. Conditions here would be that V1 plus G2 is equal to G, and then V1 plus N2 is equal to N. And so this means that like I can try to inject into here, and then the cohomology of this space is controlled by the cohomology of sort of smaller moduli space. That's the start of the induction. Okay, and sometimes just for index-dependent reasons, it's easier to work in Borel more homology. And there's the same idea. So for me, homology is always Borel more homology. So anyway, don't worry about it. You've never seen it. For compact spaces, it's the same. So I can also look at the long exact sequence in Borel more homology. Try to do the same idea. So the idea being that if this or a more homology group vanishes, then the homology of this is generated by push pulls to the boundary, and that's another way to phrase the induction. Okay. So how do we start the induction? This is the way we start is we borrow from the topologists. So this is their part of which would be the R, part of which would be to Putnam, Church, R, Putnam, and part of it is to the same part of this is these guys do to Marita, this guy, Suki. And what it says is that the Borel homology, or the convexly supported cohomology, is 0 in the following cases. Whenever K is less than 2G, if N is equal to 0, 1, or K is less than 2G minus 2 10, and 2. So I think this part here is the original virtual cohomological dimension of the mapping class group argument. So that's from R, and then the improvement by these authors. And actually, since we're here in Frankfurt, Wong also improved this when N is 2. Wong is a student here, I think. Let's see here. And we don't use it in our proof, but I can imagine the next case when K 15 that his improvement will be useful. Okay. So as I mentioned, there's no known algebra geometric proof of these results. So if anyone knows them, that would be nice. but we really need this help from the topologists.
Very stupid question. What's the cohomology theory you're talking about there?
Pick your favorite. What's your favorite? Yeah.
Okay.
Analytic cohomology, QL coefficients.
Okay.
Yeah. That's why I'm talking about Motivic.
But is it also true for the torsion, or do you have to?
No, two coefficients. Okay. So for this says that for G G large topology tells us how to start the induction. To get the base cases, we need to do algebraic geometry. And that's the idea behind all of the roots of the theorems I just arrayed, is that we need to do hard work for small d and n. So for example, Bergstrom, Popper, and Payne did this by counting points over finite fields. This is like very difficult technical work. I want to make one observation that makes this problem slightly easier, is that to actually do the Arborello-Fernalba induction, you don't need something so strong as the compact and squared cohomology vanishing. What you actually need, so idea is to start the induction. You actually need just say the K-graded piece of the wave vector to vanish, or maybe in Borel more either this as weight minus K, H to K, yeah. And this is sort of just Hodge theory. Basically, if you look at this long exact sequence in squared cohomology, this is the long exact sequence in Hodge structures. And if you look at the weights, you don't need all of HK C of M to the end of that. You just need this small part of it to vanish. And this, interestingly, is the part of cohomology that's accessible from an algebraic geometry point of view. This is perhaps like one way to say this is that this is where the cycloclass map lands from the Chow theory. So we have the cycloclass map, which takes Chow classes on MDN and sends them to more homology classes for distance. And I want to get at the vanishing of this using what we know about the Chow theory of MDN. So to do that, I need some idea about like how to understand the image of these maps. So insert the following definition. So this naming that has been coined by Bay and Smith, but ideas similar to this are all around the literature. So let X be a space, I would say like maybe a quotient stack, or something that you can reasonably compute the Chow theory of. So we say that X has the Chow unit generation property. The shortest is PK GP. I haven't asked them about this capitalization choice that they made. But yeah, it's an interesting one. So CKGP. If for all y, the exterior product map is projected. Okay, so where does the name come from? Well, this is basically the map in cohomology that gives you the Coulomb isomorphism. And we're just saying that we want it to be projected, so it's just a generation property. And it's saying that you don't necessarily have a Coulomb formula in Chow exactly, but at least every cycle on the product should be coming from cycles on each side. Okay. That's the definition. And one can group the following another. So let X be an open substack of a smooth property on stack. Call it X bar. If X, so if the open part has the CKGP, then the cycle dot map projected. Thanks. I really only worked in one other minute. So okay, so let's look like. So notice here I've taken this direct sum over all K here, and I've taken the direct sum over all J here. But here there's odd stuff. But here, like the cyclops map is like degree something, right? So here I'm saying that this map is projective, but its image only lands in the hidden part. So this means that all of this odd weight, all of the odd pure weight stuff will vanish whenever you have this CKGP property. So this should tell you that this property is very strong and hard to find. So the upside is that if you have this CKGP, then your pure weight homology in even degrees is K in algebraic, and in odd degrees then. I mean, that's like a really strong thing. But it's still easier, I think, to write down spaces that have that property than it is to write down smooth, proper, leave up its stacks over the end of it.
Are you going to talk about the data?
I'll give you a heads up, yeah. I could say that with very slightly different hypotheses, that this lemma has been proven by many people. So like, I think I learned first reading in the motives book, there's an article by Janssen where he proves that if X is compact. His statement is roughly if the cycle class map is injected, then it's certain. And there's other similar ideas by many people. So yeah. the idea proof idea is that you use this Tau-Kunis generation property to write the diagonal of x bar times x bar as the following composition. So here I'm taking the dimension of x and c, and the point is that gamma, this first class, is supported on x bar times x bar minus x. So it's think about it as being the boundary divisor on this side, and this delta L cycles. These are sort of products type cycles. So delta L is a linear combination cycles of the form BL times WT minus L, where BL is a subvariety of X star of codimension L, and similarly WT minus L is a subvariety. I guess maybe I want the dimension of X bar. Okay. So basically, what you do is you just think about what the CKGP implies. You write down this decomposition, and then this diagonal as a correspondence is going to act by the identity, and you just analyze how each piece should act, and that's how you see how you get this together. So what we want to do is use this topologist result when G and N are large, and use the CKGP when G and N are small. So our hope is that MGN has the CKGP when G and N are small. And this is sort of only possible if G and N are small. So what has the CKGP? So some examples are affine space, AN, and then more generally affine bundle over X, where X has the CKGP, and then similarly, so spaces that are stratified by spaces that have it. So, for example, Pn is stratified by ANs, and AN has it, so Pn's going to have it. Grassmannians, Grassmann bundles over things that have it, etc. And then also a fancier point of view, although the proof is basically the same, is quotient stacks that are approximated by spaces that have it. So for example, BGLN, ESLN, and then a little extra argument against BGLN. So what I mean is that like BGLN, topologists would say that this is some infinite Grassmannian, and infinite Grassmannians should happen, right? You just take the limit here. You can prove this rigorously using Tataras and editing Rand's equivariant intersection here. Okay. So we've seen plenty of examples, affine spaces, PN, Grassmannians. And then this sort of allows you to take quotients by these groups and still manage to have the CKGP. And luckily, the moduli space of curves with low G and slow number of arc points often looks like a Grassmanni bundle mod group, something like that. So here, I'll keep this with Anna in 2022. So consider the following table. That. Okay, so for N, M1, C or G, and G up to 7, we have that MGM has the CKGP. So let me just say a few words. For genus 0, this is very much not due to us. And this is this is kind of, I would say, classical fact that you can write M0 and by hyperplane document. I would attribute the genus 1 results to Belrusky and his PhD thesis, explicitly stated in this way. And then some lower number of mark points results are in the literature already, but we tried to push this as far as we can. So the first paper, or one of the papers in Canada, we did this, except the CFG would have been 0, but then we improved to 3, which is what was necessary in the next step, I would say. Okay, so the point is that we use the topologist results, then in the complements of where the topologist results don't hold anymore, we use this, and then we just run the induction. And actually that's how you can do the proof. Let me explain a little bit about how to prove theorems like this. Okay, so I just pick a random example. So it's going to be M5. So how do we show that the modified space of genus 5 curves has the CKGP? Well, first you stratify diagonality. If you show each stratum separately has the CKGP, then you can glue it together in a minute. So I'll tell you about the general stratum. So the general curve of genus 5, I'll say M5 cert. For the general curve of genus 5, the complete intersection three quadrants. So all we have to do to understand this locus is to look at the space of quadrant B4, which is the choice of three quadrants in B4. I've counted the number of quadrants for you. So I take a net of quadrants. I remove the ones whose base locus gives rise to not a smooth curve. So maybe a singular curve or not a curve, etc. And then I just have to portion out, because this is a canonically embedded curve, I just portion out by PGL. Okay. So I want to show that this thing has a CKGP. Well, this thing is an open subset of a Gauss-Lund bundle over BPGL here. And the point is that this has a CKGP. And this is a Gauss-Lund bundle. But at least an open subset of a Gauss-Lund bundle. And Gauss-Lund bundles over things that have the CKGP, and then removing, going to an open subset also preserves having. So it's actually quite simple to show that when something has a CKGP, it's usually not that hard to show that it does have. But not so common to find these spaces. Okay, so we have to do something like this on the next locus, which would be the locus of trigonal genus 5 curves. And that you can write a sort of similar presentation. I guess all the curves should lie on a good group surface. And it's a pretty similar thing. And then the hyperelliptic ones, actually that works in arbitrary units. And then you have to figure out how to add mark points. The general feature of this is whenever you can prove that something does have this CKGP, you basically proven or used that someone else has proven that the space is unirational. So you should stop expecting to be able to do this quickly. Yeah.
But where you cannot prove it is because they don't have that property, or because you can.
So there are obstructions. For example, one obstruction would be if your space has a compactification that has a holomorphic form on it, then you cannot have a CKGP. That's one obstruction. So that says that M111 bar does not have a CKGP, and that's so we have sort of a precise result here. There are obstructions. There's also cases in here where unirationality is known, but we can't prove the CKGP yet because some locus is difficult to deal with. So, yeah.
But you might guess that whenever the Kodaira dimension is negative.
Yeah. I think it's reasonable, yeah.
For the conjecture, CKGP is only negative Kodaira?
At least for MG, yeah. There's not so many cases. Okay, so this is basically the whole idea. We basically we use this topologist result, we use this, and then we can now run this induction. And what's missing, so what's left? Is a bit of extra work in genus 1 and 2. Basically, there's some cases that the topologists don't cover that also we don't cover here. And luckily, in genus 1, Peterson and Gessler and others, they take care of it for us. They basically completely understand the cohomology of M1 bar. And in genus 2, we use some results of Dan Peterson about cohomology of moduli with Euclidean surfaces, and we leverage that to get what we need in genus 2, and that takes care of all of the base cases for the induction, and that's how you prove these second theorems. So in my last few minutes, I wanted to to say sort of, can we go beyond the Langren's prediction? So what we've shown now is only certain motives can appear in certain cohomology groups, but the natural question is, do they? Right? And I said earlier in response to a question that they do appear in some MD and R. But for which G and N do they appear? It's not a question. And actually, we can say a lot. So the theorem says that the 11th cohomology group of MDNR is non-zero if G is 1 and N is at least 11. That's the only time it's not zero. So you almost always get vanishing. And similarly, we can say something similar for H15. So the better way to state it for H15 is that H15 0, say, if you're doing Hodge state, equals 0 unless G is equal to 1 and N is equal to 0. So you actually get much more vanishing than was predicted by the Langren's program. And the idea, the proofs of these theorems is to go beyond the Arborello-Fernald induction. So the Arborello-Fernald induction uses the long exact sequencing cohomology for MDN bar as a boundary. But the long exact sequence is really equivalent to sort of a tiny bit of data from the weight spectral sequence for MDN in its compaction data. And if you just look at the first two maps in the weight spectral sequence, that's how we prove these theorems. So I can write down what the first two maps are. So the Arborello-Fernald induction studies the following map. This is a fancier way of writing the cohomology of the normalization. Here I'm summing over all stable graphs with one edge. So I take the curves that have, like I said before, just the one node. I sum over all of these, but this is just the first map in a chain complex. So you can just go to the ones that have two edges. There's some monotones and you can keep track of the representation of the automatic group. The graph on the edges. So now this is actually a chain complex, and of course you can keep going. And this would be sort of telling you the part of the weight vector sequence that computes the weight K part of the cohomology of MDN. So the idea is that we just have a complex here. The arbor for now that actually studied when this first map is injective, but it's a complex. So if you want to show that something here is 0, you should just show that this whole thing is injective. So we study when this map is injective by hand. So that's the idea of this theorem. And then the last theorem I want to state, which is kind of interesting, because it reveals something that's maybe surprising at first glance, is that if you look at homology, so you can think of this as high codimension cohomology. This is topological, so it's generated by the topological classes, which all of us have avoided defining so far. So for K is a most 14 even. And so the Langlands prediction said that for K in the most 14, K is about 20 even, that H upper K should be Tates. But this is like the odd conjecture history. We're saying, okay, actually we can write down specific algebraic cycles here, and they're tautological cycles, which is a really nice epicycle. The interesting thing is we don't know how to prove this if I move this up here. And at first I was quite surprised that we can't do it in cohomology, we could do it in homology. But if you think about it for a few more seconds, you realize that if you knew it in cohomology, then it would be automatically true in homology by the hard left test. Yeah. So this is somehow the fact that we can prove this is tautological, but we can't prove H upper K is somehow related to one of the standard conjectures. But it should be easier than that. So yeah, that's maybe I will just end here. So thank you.